Oh, they're actually the hardest thing. It's really you both back. So we'll get that. What should introduce you then?
We're still in chapters 12 and 19. Nucleophilic addition to carbonyls. This is sort of where I left off last time. All right, let's hydrate formation. You all have used the word hydrate before. You've heard the word hydrate before. I don't think I actually use this word. I think start using this word in RO1. When you add water across a carbon-carbon pi bond and alkene, you get an alcohol. That molecule is an alcohol. But you've hydrated the alkene. So this reaction is reversible, as is hydration of an alkene, but this reaction is really reversible. So basically, any compound you dissolve, any carbonyl compound you dissolve in water, you know, there's a trace of hydrate at any given time, right? Again, you keep drawing this, I keep drawing this. It's like we have this one molecule doing something. Remember that you've always got a lot of something. So if I dissolve a millimole of acetone in water, right, I've got something like 10 to the 20th molecules of water, or of acetone, sorry. Right, so even if this equilibrium constant is like 10 to the minus 15, then I've still got like a million or so at any given time hydrates. Like it's mostly carbonyl, but I've got a lot of hydrates. Anyway, I'm just trying to make sure you guys keep some perspective on the molecules, that it's not ever just one molecule or a couple of molecules, it's always a lot. And as you guys progress, most of the way we study molecules is using statistical analysis, right? If I say the molecule does X, it really does sort of a Gaussian distribution around X. Okay, so this is reversible, and under almost all cases, like it's really notable when it's not the case, this side is heavily treated with water, all right? So basically, if I now do really focus in on one molecule, so I'm not thinking about this as a population of molecules. If I focus down on one molecule, it's going to spend, 99.7889% of its life like this. Every now and then it's like this, right? So it'll form, it'll live like this for an instant, and then go back. And like I said, there are two. You can get to the hydrate either by an acid catalyzed addition or a base catalyzed addition. And we're going to see over the next couple of weeks a bunch of mechanisms where we're working in acid or we're working in base, and the reaction changes accordingly. So this is a result of a nucleophilic attack. Right, so the water, and so this is not a mechanism, I'm just kind of giving you the outline. The water is adding to the carbon, the positive end of the carbonyl. And there's really two ways we can get, there's two ways to add a nucleophile to a carbonyl. And I'm just drawing acetone here, right? So this is acetone, it's a ketone. You guys know acetone. If you've ever removed fingernail polish, maybe paint, that's acetone. You can buy acetone at the hardware store, in the grocery. We clean glassware with it in here. So you guys know, the substance acetone. But this is all true of pretty much any carbonyl, right? An aldehyde, a ketone, carboxylic acid, an ester, an amide, whatever. These carbonyls pretty much work the same way. So if we have a strong nucleophile, so this is going to be something, probably has a negative charge. If it doesn't have a negative charge, it's a fairly strong base. And this reaction, if you have a strong nucleophile, it's driven by the nucleophilicity of the base. Like what makes this reaction happen is the nucleophilicity of the base. So we're going to have a couple of electrons here. And those are going to add into the partial positive carbon of the carbonyl. You're going to pick 2 electrons up onto the oxygen. This will give us right. The key here, the key thing to recognize is that this strong nucleophile is a fairly strong base. So that reaction's run under basic conditions. Like I said, when you do mechanisms, you want to look, you want to identify, is the reaction being run under acidic conditions or basic conditions or neutral? And you don't want to have something that contradicts that, right? If a reaction's run under fairly neutral conditions, it's hard to create a lot of strong acid or base. If a reaction's run under strongly basic conditions, it's hard to create a strong acid. But if it's under strong base conditions, we can make a strong base. Right? Strong bases exist under strongly basic conditions. All right, so the other way, I think this way you guys might have come up with that. The other way is to protonate the carbonyl first. All right, if you protonate the carbonyl first, that makes the carbonyl much more electrophilic. So now you don't need a strong nucleophile. You can have a weak nucleophile. It's still got to have some electrons, right? And so that will, again, attack the carbon in. I should say these are usually reversible. This reaction is driven by the electrophilicity of the protonated carbonyl. Right, so that protonated carbonyl, this is a strong acid. So the reaction here is being run under acidic conditions. Right, so under acidic conditions, we can't make a strong base. I see a few nods, people looking at me. This always, I usually gloss over this because this is just like kind of natural to me at this point. This intermediate is a strong base. You got an O minus, the O minus isn't delocalized anywhere. So that's like hydroxide or methoxide or something like that. It's a strong base. You can't make that sitting next to a really strong acid. All right, so your intermediate needs to be proton. And this really does sort of run this way. So under basic conditions, I don't want to say that. Hang on. Sort of a sheet on this. Just as you look at these, right? If the reaction is being run under basic conditions, you can have deprotonated oxygens, you can have deprotonated or neutral nitrogens. Remember, nitrogen's usually a strong base, and neutral nitrogen's a strong base. Under acidic conditions, you always want the O's protonated. The N's are usually going to be protonated, right? So the intermediate here, we've got to have that oxygen. Nucleophile is going to attack a carbonyl. The carbonyl oxygen is going to become single bonded. In the mechanism, does the proton go on first or not? Like this up here, we're going to eventually work this up, right? We would eventually step 2 be to add a proton. Like you're always going to eventually neutralize everything. So like you're going to see a reaction where it's basically a carbonyl plus some reagent, and you're going to end up with an alcohol. And the question you have to ask yourself, do I protonate the oxygen first or last? If the reaction is being run under basic conditions, you protonate it last, right? If under basic conditions, you don't have any protons with which to protonate the carbonyl oxygen. Under acidic conditions, right, it's acidic. We do have protons. So you're going to protonate the oxygen first, then the nucleophile adds. All right, that's a bunch of general stuff. Now I will do let's do the mechanisms. So while I move the cart here, try to figure out where I try to put my computer, try to work out this mechanism. Hydrate the carbonyl under acidic conditions. Will that work really good? All right. So one, I told you, like the headline up there says acidic conditions. On exam 2, I'm not going to say under acidic conditions do this. You're going to have to identify that. How do you identify that this is acidic condition? You got an acid in, right? So you have to know the structure of acids and bases. You see hydroxide, and again, like I'm going to try to limit it. I always give myself an out by saying I'm going to try, but I'm going to try to make it acids and bases you guys have seen, right? Just like all the reagents, there are way more acids and bases than you guys have seen at this point. But if you see HCl, you guys have seen that since you were, I don't know, second graders when they start HCl these days. Yeah, I know it's not. But you've seen HCl for a long time. You've seen hydroxide for a long time. You should be able to tell when that. Okay, so we're going to do this under acidic conditions. That means we're going to protonate first. And when you protonate something, you always protonate with the strongest acid. So the first step here, the electrons on the carbonyl, right? The arrow is going to start with electrons, go to the proton. You got 2 choices here for proton. You could grab a water proton. You could grab an HCl proton. Water is a weak acid, HCl is a strong acid. So grab the HCl. If you grab the water proton, you make hydroxide. Okay. That would be a strong base sitting next to a strong acid. That's not going to happen. All right, so the carbonyl grabs the H, you get a chlorine ion. This is a reversible reaction. Intermediate, you get a chloride ion, right? That chloride ion could take that proton back, you get HCl and acetone. That happens. Like that, these molecules kind of ping pong back and forth here thousands of times before anything useful happens. The useful thing then is water, which is a weak nucleophile, right? Water is not a strong nucleophile, but it's a weak nucleophile. The water then is weak, but this is now strong. Pretty much every if I say something's a weak acid and something else is a weak base, the weaks in there mean that they're not going to react with each other. A weak acid needs a strong base. A weak base needs a strong acid. So if I just have water and acetone, right, that's not going to be a very fast reaction. They're both neutral. So water then acts here. The molecule you get to just follow the arrows. So we're going to make a bond between this O and the C, and we're going to break the CO pi bond. And there will be great temptation on your part to go straight from here to there. Right? You'll be like, oh, we take a proton off here first and make hydroxide. Or water attacks and I just get one H. You guys get in a hurry. Some of that is stress on an exam, a timed exam. Like, don't you like it when your professors give you a hard time for rushing at the same time they're giving you a timed exam? Right? That's fun. You have to finish this in an hour, but go slow. So you want to go as fast as you can without hurrying. You don't want to hurry. Hurrying implies chaos. You just want to go as fast as you can under controlled command. Water attacks here, there's nothing to pull this proton off. You don't have a base to pull this proton off. Protons never just pop off molecules. Right? Something has to pull them off. So now you're here, and I don't care what you do, like to regenerate HCl, you have chloride grab this proton. In reality, what would happen is a second molecule of water take that proton. And that would also produce H3O plus. Remember that H3O plus is the strongest acid you can have in one. So honestly, yeah, sorry, I'll come back to you. Honestly, when I say HCl and H2O, I'm saying H3O. Right? HCl will protonate the water, you'll have H3O plus. If you wanted to do that first, if you just wanted to take these two and make H3O plus and chloride minus, I would be thrilled. That's actually what happens. And then the oxygen takes that proton. But if you just want to use HCl, if you want to use the acid I give you, that's fine too. I mean, I might write it as H3O plus, I might write it as HCl or sulfuric acid. You guys should know separate, I mean, this is a lot going on here. So if you can demonstrate to me that under acidic conditions, you're keeping everything protonated, you're attacking with weak nucleophiles, I'll be thrilled. You do need to keep in mind in the back of your mind, you know, not necessarily for me grading exam 2, but when you do Gen Chem 2, when you do biochemistry, when you start actually working with aqueous systems, if you put a strong acid in water, you get H3O plus.
Yeah, I was asking why won't this be on?
So what happens here is like, what's going to, like, think about this. Sorry for fluttering out the orange color. Think about that intermediate. Something's going to grab that H. Up here at the top, I pointed out when you're going to protonate something, you always protonate with the strongest acid. Well, when you're going to deprotonate something, you always deprotonate with the strongest base. So there's two things going on. Water is a stronger base than chloride minus. And there's a lot more water. Like if we actually go in and do this reaction, this is catalyzed, right? It's HCl catalyzed. So we put like a drop of HCl into a beaker full of water. So not only is water at stronger base. Like we had one water and one chloride, you'd still expect the water to grab the proton. But there's actually like 10 billion water molecules for every chloride. So this proton is a lot more likely to encounter water first. Believe it or not, we will come back to that a lot this semester. All right, so that's the acid catalyzed hydration. So we take a carbonyl, we protonate it. Now water can attack the carbonyl. We get a protonated intermediate. This is just the protonated acetal. Sorry, hydrate. This is that's the hydrate. That's a protonated hydrate. So protonate, attack, deprotonate. Would it be fair at this point for me to ask you to draw the reverse mechanism? Like the hydrate going back to the carbonyl. Act like your answer to me asking you, is it fair if I ask, is always no. Act like that's not always no. Right? None of you think that's good. It actually is. And the reason is the reverse mechanism is literally the reverse. So to go in reverse, why don't I do that down here for a little bit? See it. There's something called the principle of microscopic reversibility, which I've always thought sounds cool. It's just thermodynamics. You can't create or destroy energy. And that's going back to kindergarten. Right? That's like a fundamental fact of the universe. You can't create or destroy energy. So if somehow, like, remember that these all sort of represent energies, like each of these molecules has a certain energy associated with it. If I could go from this starting material to this product through one path, and then go from the product back to the starting material through a different path, those paths aren't going to have the same energy, and I would like create or destroy energy, and I would either be a god or I'd be wrong. You can take your pick as to which of those is more likely. So the reverse mechanism has to go back through the same intermediate. So what you do here, let's do this with H3O plus. Right, we protonate one of these oxygens. This mechanism is the reverse of an acid catalyzed dehydration of to make an alkene. Yeah, there's glare, sorry. All right. Now, and we get water. There's water made here. Now the water leaves. There's the protonated carbonyl. Water takes that proton, and we get to the carbonyl. The intermediates are exactly the same. So carbonyl to hydrate, neutral carbonyl, protonated carbonyl, protonated hydrate, neutral hydrate. In the reverse, neutral hydrate, protonated hydrate, protonated carbonyl, neutral carbonyl. So once you have this mechanism going forward, you have the mechanism going backwards. And I understand that like that, getting it forward is hard. Questions about that? The lighting in the room is not great. Should give you guys opera glasses at the back. Yeah.
Wouldn't that create H3O plus in the last step?
Yeah. So I started with it here. This is basically H3O plus.
So it regenerates.
Yeah. The catalyst gets regenerated. I probably should have used H3O plus in the first place. Like I said, you could have used HCl here, and then you'd regenerate HCl.
What do you think, Sean?
If you have HCl in water, you have H3O plus. All right. All right, give that a try. What is the mechanism to hydrate carbonyl under basic conditions? Or I should say base catalyzed. I just want to point out, you guys did my homework harder with that one. On the board of. I'm asking you to draw some lines on the page. You guys are supposed to solve homework. Like, I have no idea what class that is. I was reading it because I thought it might have been the biochem class in here earlier. Doesn't sound like biochem. If it's got feelings, I don't want to know about it. All right, so under basic conditions, I was kidding. Not in here. So under basic conditions, right, we have a strong nucleophile, a strong base that's going to attack first. That's what's going to drive. So over here, what drives the nucleophilic attack under acidic conditions is how electrophilic we make the carbon. All right, so if you just think about this neutral, nucleophile, electrophile, one of those has to be souped up. If you just leave a weak nucleophile and a weak electrophile, nothing really is going to happen. So here, have my color code. What's going on? What drives this reaction is the hydroxide. Remember, right? If something's going to be a nucleophile, it's going to be the stronger nucleophile. So water is a nucleophile, but it's weak. Hydroxide is a nucleophile and it's strong. So the hydroxide just hauls off and punches the carbonate. Right? We have organic chemistry, like a lot of sciences, was very masculine for a very long time. So the language of organic chemistry is all attacks. It's very macho. And it's less and less, but we haven't gotten rid of the language. We have a lot of women organic chemists. They haven't cleaned up our language. So we call this an attack. All it really is two atoms. You've got a hydroxide that really wants to give its electrons away. And it's going to collide in solution with a carbon that would really like to take some electrons. All right. So draw what these arrows give you. These arrows don't give you the hydrate straight away. We're going to attach an OH to the carbonyl. This O is going to stay or become negative. So this mechanism is a little bit easier. Right. Now we have a deprotonated hydrate. To get to the hydrate, we just have to protonate it. So what in all of this mess is going to be the strongest acid? Waters, right? Don't draw anything in here. One thing that happens a lot, I saw this many times on the exam. I will see it on exam 2. I'll see it the rest of my career. But a lot of students, when they're working an exam, again, this is probably a little bit of panic, will invent a reagent that's not there. Right? If I had sulfuric acid, it would do something. If I had bromine, it would do something. Yeah, it would, right? Yeah, if you added sulfuric acid to that, that would be the thing that protonates it. But if it was there, I would have told you. Right? So if I ask you a mechanistic question, I've told you what's in. Right? You're not gonna. If I just say, what would that question be? Draw a reaction, Maybe I'll put that on as something. Draw a reaction, give me the product and the mechanism. And you'd better get that one right. All right, so don't add anything here. You don't have HCl to throw in here. You don't have sulfuric acid or H0+. You've got water. And so, all right. Oh man, I guess that went here. Sure. Right, so water is your strong acid. The strongest, it's not a strong acid, it is the strongest acid in there. But now this negatively charged oxygen, that's a strong base. So that oxygen takes the proton, that gets us our hydrate, and it regenerates OH minus. Right? So it's a hydroxide catalyzed addition to the carbonyl. Yep. Is it a chiral carbon? It is not. But no. Okay, so that's a good question. I want to get to the real question there, but that is not like if you got 2 OHs on there. So with acetone, you already had 2 metals, so it doesn't matter. It wouldn't be even if you added 2 different things, it wouldn't be chiral. But it is possible to make a chiral atom, not with 2 OHs, but we're going to make acetals here in a minute, and they would be. So this also comes up. I should review that on the exam, I guess, right? The shape of that carbon. Well, what is the shape of the carbon? One person. Trigonal plane. It's an sp2 hybridized carbon. It's flat. Right. So the hydroxide can attack from here. It can attack from the backside, and there's nothing physically, making one of those a better pathway than the other. So it would be stereochemistry always matters. I guess is what the short answer to your question is. Stereochemistry always matters. If there is stereochemistry, it matters. But for there to get a different amount, to get one enantiomer over another enantiomer, there has to be some chiral element in the reaction. Either the reagents have to be chiral, the catalyst has to be chiral. At some point, something's got to be chiral. So like if we had, for instance, this is a complicated. Yeah, no, that can be a metal. Let's add a grignard. All right, total just. I introduced grignards last time. I'm going to talk a little bit more about them this time, probably. So now that grignard is going to attach the carbonyl. Again, this is a base, right? So coming back over here, you got to identify, is this a basic reaction or an acidic reaction? And a grignard, you have known about grignards for like maybe a week at this point. Can't remember if I talked about them last Wednesday or not. If not Wednesday, you've known about them for 2 days. So is that a base or an acid or what the hell is that? It's a base. Okay, so again, this is going to react. You can imagine this reacting as if the carbon is negative and that magnesium is positive. Right? if hydroxide is a strong base, a negative carbon is going to be an even stronger base. So this is under strongly basic conditions. The grignard is going to attack before you protonate. And so when I say that, we're going to get this attack of a grignard. And this is where mechanisms really kind of fail. Right? I could draw that carbon getting in there like nothing. I don't know if any of you ever played football. Like I don't even mean like organic football, it's like out in the backyard. You draw plays in the dirt. Like some X goes down here, right? Like in reality, you're running against some guy who's trying to take your head off and the ball's gonna fly through the air. Like it isn't like you can draw anything you want in the dirt and you're always gonna score. In real life, that's not the way it works. So I can draw this arrow coming in from anywhere. But think about what it's got to actually do. This carbon has to either sit down on top of the pi bond here, or it has to come from the other side of the board. And in this conformation, which one of those do you think is more likely? It's going to come from behind, right? If it comes from in front, it's got to get by this T-butyl group. And so the answer would be, you would get, right, so. Right, you get both of these. You probably would get both of these. I had this conversation with a few of you in office hours, so it's a necessary diversion probably. Let's say this starts at 100% E. Right. What that means, EE is enantiomeric excess. If you don't remember from Morgo 1. It's how much in excess one enantiomer is over the other. This molecule's got one chiral center, so it has one enantiomer, right? You could have the T-butyl group back there. All right. 100% EE says the enantiomer drawn is in excess over the other by 100%, which means it's all that molecule. So if I have 20 moles of this substance, I have 20 moles of this enantiomer. And then I might ask, on the other side, what's the EE of this thing? Right, so this is the test-taking strategy I discussed with some of you. There really are three answers that are ever possible. Right, one answer is whatever this is, right? So like think about a pure SN2 reaction where you get backside attack. Right, whatever the EE of the starting is, that's the EE of the, it'll invert perfectly, right? Every R turns into S, every S turns into R, and my EE stays the same. So one answer is to just tell me whatever my starting EE is. The other possible answer, which was the answer on exam 2, was 0, which is a racemic mixture. I have equal amounts of the two. And this goes to up at the top, right? If you have a planar, actually both these reactions, both hydration reactions, this is your original question that you might have forgotten about. There's nothing chiral anywhere. I've got a flat molecule reacting with an achiral molecule. There is no reason for the nucleophile to come from the front or the back, top, left or right. So I'm going to end up, if I end up with enantiomers, I'm going to end up with a 50-50 mix. And even if you start with a molecule that's got chirality, if that chirality is lost during the reaction, so the question where I asked the EE on the exam, you have a chiral bromide, but the bromide leaves and you get a cation and it's flat. So at that point, the nucleophile can come from either direction. And the answer was 0. So if you see this question, and this applies to real life too, your answer might be whatever the start was. Doesn't have to be 100, but plausibly it could be, right, whatever the start was. It could be 0. You could tell me 0 plausibly. There is no other number that makes sense. The other answer that might make sense is somewhere in between. And the answer here is this would be somewhere in between, right? That, or in terms of the ratio of addition, most of it is gonna look like this. The phenyl is mostly gonna come from the backside because of that T-butyl sitting in front.
Are those dice?
They are. Thanks. I was gonna just try to slide right by that. The EE of that would actually be whatever the start was. And the EE of the other one, but I'm saying so that's a good question. If you're missing it, which I did when I started this, these two molecules are not enantiomers of each other. They're diastereomers. That, right now we've got two chiral centers. We've got this one, the oxygen, we've got that with the T-butyl. The T-butyl doesn't change. So we've got this one and that one. One stereocenter stays the same, one changes. Those are diastereomers. But you could not tell me, it would not be fair to me to ask, let's say, so I don't ask, let's say I actually catch this mistake before I give you the exam. Like, it would not be fair to me to ask, what's the ratio of these? Right? You could tell me there's gonna be more of that, less of that. You could not predict, especially given no reaction conditions, you could not predict how much of one, how much of a difference there would be. It's possible it's 100%, it's possible it's like 1% difference. So the answer would be, if this was an EE question, you're never going to be able to say that would be 17, starts at 91, what's the EE? Unless I give you some rotation data or NMRs, there's no way for you to tell me what the number is. So for any of you who wrote down an actual number, like I said, you're essentially guessing at that point. And you're guessing 1 out of 100. That doesn't, so 0 is a plausible answer always, racemic. The same as whatever it started with. Or if you're going to tell me that it's not one of those two numbers, you need to just tell me it'll be non-zero but less than its sum. The other thing on the Grignard, there's always, when is the question you have to ask, when is the stereochemistry set? You might hear me say that at some point. When does the stereochemistry get set? So if you're trying to answer a question, what is the EE? What is the ratio of diastereomers? You need to consider at what stage in the mechanism does the stereochemistry get set? If the stereochemistry gets set when the molecule is flat, you're going to get a racemic mixture. If there's a reversible process, it will equilibrate. So let's say one of these dice, and I have not given any, I came up with that out of thin air. So I don't know which diastereomer would be more stable. You'd have to do Newman projections and all that stuff, right? But let's say one of them is a lot more stable than the other, but it doesn't form first. You guys remember this from dynes, right? Kinetic product versus thermodynamic product. If this reaction, if this step is reversible and the kinetic product is not the thermodynamic product, the conditions are important. Like, will it reverse? Will it not reverse? In this case, this reaction is not reversible. Okay? We have a really super strong base here. This O minus is a strong base. Notice it is not super strong. These are technical terms. Okay, so I have a super strong base attacking a carbonyl. I make a strong base. That really favors the right. To imagine going backwards, this O minus would have to make a pi bond and kick out a methyl minus, or it would have to kick out this big group minus, or it would have to kick out the phenyl minus that went in. None of those are plausible. You'd have to have an O minus, which is a strong base, but things that exist basically kick out a leaving group that is one of the strongest bases known. All right, so the fact that this is irreversible, it does not matter at all. The product, it does not matter to the product ratio at all which one is more stable. And this is a really hard thing to get. You guys will forget this. I forget this all the time in my own work. I'll be like, well, this reaction will give me the product I want because it's the most stable. And I forget that that never comes into it. The only thing that matters here is what's the fastest path to get the phenyl group onto that carbon. And that is from the back, away from this p-butyl shield. Right. So again, if the reaction were reversible, it would matter. So what might be reversible? Predict what happens if I mix those reagents together. Sorry. I didn't kick you, did I? Roll over your foot. Is this reaction under basic or acidic conditions? Basic. Methoxide is a relatively strong base, like hydroxide. If you guys see a localized charge on O, it would be some chance that's a strong base like hydroxide. So what this would do, the methoxide would attack the carbonyl all over the map with colors. Now, is that addition reversible?
Yeah, I guess the minus on the could take.
Right. So you go from an O minus to an O minus. Those are roughly the same. All right. So this reaction does reverse. And so what would matter then, like trying to figure out, right? You've got a stereocenter here. This is sort of going from the original question. You've got a stereocenter here, right? O minus is not methoxy, methyl is not this alkyl group, 4 different groups. What would matter, what would accumulate the most there, again, would depend on stability. Because that's reversible, it would eventually get to the more stable diastereomers. Now, it turns out that's not actually going to get you to anything more stable. Right? That's the first step of something we're going to do later. You would protonate this, right? The O minus could take this H. I'm going to do this kind of quick because I want to move on to something else. This molecule is called hemiacetal. We're going to do acetals next. So a hemiacetal has a carbon with an OH and an O alkyl. And it's the intermediate in going from a carbonyl to an acetal. I'll tell you again, I'm going to tell you the rest of the story in just 1 second. Usually, and when I say usually in this class, always, well, until we get to carbohydrates, that is usually not isolable. This hemiacetal is either going to go on to the acetal or it's going to come back to the carbonyl. But you can make it under basic conditions. You can't make an acetal under basic conditions. I'm going to go back to acetone just to keep us from drawing lots of molecules. So this is chapter 19 entirely, I think. I think this is only in chapter 19. If you're wondering where this is, don't think any of this is in chapter 12. So we've made an acetal from a carbonyl. An acetal is it a reduction or an oxidation? Going from the carbonyl to the acetal. Do I hear what was the other? Neither. All right, count. We get this carbon has 2 bonds to a heteroatom. This carbon has 2 bonds to a heteroatom. I should also say you get water. You lose water out of this. It's a plus, not a man. What else should I say about it? Yeah, it's neither an oxidation nor a reduction. A couple of questions came in about like when I say it's a reduction or an oxidation, do I mean it's the whole molecule? Am I talking about the whole molecule or an atom? And colloquially, if a chemist says this is an oxidation, they're talking about the entire molecule. Really, you should specify the atom, right? So that methyl stays a methyl, that methyl stays a methyl. That's obviously not changed. So there's really only one atom in this molecule that changes anything. And so if you figure out that that atom is not oxidized or reduced, then it's neither. If it was oxidized, the whole molecule would have been oxidized. If it was reduced, the whole molecule would have been reduced. You can see reactions where multiple atoms change, and you've got it for the molecule as a whole. You sort of have to, right? If one carbon's oxidized and another is reduced the same amount, overall that molecule is not oxidized or reduced. Does that make sense? Like it's kind of like formal charge and charge. We do formal charge atom by atom. We do molecular charge as a sum of the formal charge.
So how does the other OCH3 get on?
There we go. We're about to have a lot of fun with this mechanism. This is when everybody really starts to love organic chemistry. No, this is a good this is a really fun mechanism. And you can't do that. You can't get to the acetal from here. So your question, how does that other methoxy get there? Right? If I've got base, right, methanol is not going to do anything in this reaction because I've got a strong base. The reaction on the top to make the hemiacetal is driven by that methoxide. It's driven by the strong base. All right, well, there's nothing for methoxide to attack here. Like it can take that proton off, but now I have an O minus. The O minus can't take the methyl. OH isn't a leaving group. There's no way in the top reaction under basic conditions to get a second methoxy group in there. There is on the bottom. So let's go through this slowly. This will pretty much be the rest of the class. All right. So first step, under acidic conditions, right? It's an acidic condition. HA could be sulfuric acid. It could be paratoluene sulfonic acid. It could be HCl. It could be just about anything. We're going to protonate the carbonyl. And we get A minus. Whatever the conjugate base of the acid is. Now, methanol adds in. This is how we get our first. Methanol in there. We have, and again, we have lots of HA, we have lots of methanol, we have lots of acetone. There's all these molecules, like there's a bunch of all of it. So methanol, just keep my color coordination going. Methanol is a weak nucleophile, like water. So it can attack the protonated carbonyl. Protonated carbonyl is really electrophilic. Key thing to remember here, don't lose protons just because you want to lose a proton. My black is running out there. Right? Methanol attacks the carbonyl. Methanol has an H on the oxygen. So the oxygen, once it's attached to that carbon, still has an H on it. You have to take that proton off, and it's gonna happen in a second separate step. Honestly, and again, this is one of those, you can use methanol then to take that proton, or you can use A minus, I don't really care. A minus is maybe a little bit more conceptually easy. So A minus takes that proton. I'm gonna write small and at the bottom of the board, I should please make it legible. Now you have a hemiacetal. HA is not standing for hemiacetal, but it does work nicely. HA is just the regenerated acid. This is also the hemiacetal, right? You've got an OH on the same carbon as an OR. Now, how do you get a second epoxy on your acidic conditions? You're going to protonate the OH. So OH is going to take that A, or that it's going to be protonated by strong acid. So now you have a protonated hemiacetal. We lose water. Get a carbocation. I'm gonna let, if you guys need to stand up or take a step forward, we all know each other at this point. I think it's visible on there. Can you draw a resonance structure for that carbocation? Let me phrase that differently. I dropped it. Can you draw a resonance structure for that carbocation? All right, so the lone pair on the oxygen can overlap with the vacant p orbital there. That gets you something that looks like this. And it looks, right? On the one hand, you've made the more electronegative element positive. That sounds bad. But unlike the carbocation in the molecule on the right, all the atoms have a full octet. So if you actually, there's a way, I don't know if you heard this in Orgo 1, I don't think I've mentioned it. We have technology to sort of take pictures of molecules called X-ray crystallography. So the distance between atoms and molecules is about what you need to diffract light that has a wavelength where X-rays have it. So if you can make a crystal, you can bombard the crystal with X-rays, you can like focus X-rays, you can get the diffraction pattern on the backside, you can solve through to what the crystal, where the atoms had to be, and that gives you kind of a picture of the molecule. This cation looks a lot more like the one on the right, right? The carbon-oxygen bond distance is like a double bond. The methyl, this methyl is in the plane with all the other like the other three methyls. So this one actually is I don't care how you draw it. You could, like, if you're drawing this mechanism, if you draw this whole mechanism, you draw that's fine. But I want you to keep in mind that that's an especially stable cation because of the delocalized charge. All right, from here now, how do we get it? So Another round. So we've still got methanol in solution. Remember, we have a lot of methanol. So it's not like you've used up your methanol. We have a bunch of methanol. The methanol attacks the carbocation. That didn't quite get us there yet. Because methanol attacks, we can't take the proton off the methanol. There's no base in there strong enough to do that. It's acidic conditions. We got to keep that methanol protonated. So methanol attacks, and that means this proton has to come along for the ride. And then take your pick. There's some water here. We could make H3O plus. There's the conjugate base of the acid catalyst. There's more methanol. Some base has to take this is maybe not making a lot of sense. One of these bases has to take that H, get us to the acetal. All right. And again, as long as you use a base that's present, I don't really care which one you use. Probably in these reactions, methanol is base, because there's the way you set this reaction up is you have a ton of methanol. Right? The reactions basically run in methanol. All right. So before we talk, I'm going to talk a little bit more about the mechanism. Before we do that, here's our equilibrium. The two sides are pretty much like you can't look at that and tell me which side is favored. Right? They're fairly close. The hydrate reactions favor the carbonyls. The acetals, though, by not having H's here, you can't pull that H off and do it in chemistry. So you have to do this to go backwards. You have to be under acidic conditions. And that's one of the nice things about the acetal. These are stable to bases and nucleophiles. So you can't do anything to an acetal with a base. You have to use an acid. So why might that be important? Let's I don't know if you guys can read that. Do you guys over there read that? The red. Did you read this black stuff I just wrote? That probably didn't help, does it? All right. Huh? Yeah, give that a little bit of thought. What happens in this reaction? The last two. Nope, nothing happens to the OCH3. Doesn't form a ring. It might. Like there is a way to get a ring out of this. All right, so here's what I'm going. I'm actually this is asking a lot. 80 minutes in. 80? No, it's not 80. how do clocks work? Anyway, yeah, you guys really trust. I'm gonna do all the sophisticated mechanism stuff, then I'm like, I don't know what time it is. On the top, we got lithium aluminum hydride. Remember, lithium aluminum hydride is a really strong reducing agent. H minus going to add the carbonyls. It will reduce all carbonyls. So it's going to reduce this ethyl ester to an alcohol. We're going to get ethanol out of it, but we're also going to get this oxygen will be an OH. So the product, I'm going to draw this in blue. But lithium aluminum hydride is a base. H minus is a base. So nothing happens to the acetal. I say weak acid here. If you quench this with like bicarb or something, so the pH stays above 7, but it's strong enough to protonate an alcohol, then you'll just get this alcohol. You will also get ethanol here, but nothing happens. I mean, you don't really care about that. On the bottom, what happens? Draw the product on the bottom. The blue reaction. Yeah. It would come off on the rotovap, right? So like it boils really low. Usually on a small molecule ester like that, you're not going to isolate the extra part. It is. I should talk about it. It's important. If you have an ethyl ester, a methyl ester, benzyl ester, that OR part, you get that as an alcohol. But ethanol, like if you think about working up a reaction, ethanol is going to dissolve in the water. If it doesn't dissolve in the water, it's going to go off the rotovap. It's actually really hard to isolate a small molecule. Yeah. All right, so on the bottom, again, you got lithium aluminum hydride. It reduces all these carbonyls. We could, if we wanted, reduce just the aldehyde with sodium borohydride. Okay, so this will get us we also get a bottom reaction. We get the diol here. All right, there's no way to reduce this ester with an aldehyde around it. So what we would normally do then is we would make that acetal first. If you want to reduce the ester without reducing the aldehyde is more reactive. So we make the acetal, we reduce the ester, and then we can hydrolyze. I haven't talked about that yet, have I? Get distracted by doing a reaction. All right, we can hydrolyze the acetal to an aldehyde. So that's the reverse of this process. So up here, where is the equilibrium? What I started to talk about, and I got in my head about the reaction. Where is the equilibrium on making an acetal? Just energetically, it's pretty close. If I take acetone and I dissolve it in methanol and I add some acid, at equilibrium, I'm going to have a lot of acetal, I'm going to have a lot of acetone, I'll have some water, I'll have some methanol, I'll have a mixture. Really what we have to go on here is Le Chatelier's principle. Right, so if I want to go to the right, if I want to make acetal, I run the reaction in methanol. Right, if I have an equilibrium that's sort of 50-50 and I add some on this side, it forces the equilibrium to the other side. If I want to go to the left, if I want to take my acetal and turn it back into a carbonyl, I add water. I run the reaction in water. All right, I'm going to tell you one last thing and then I'm going to shut up. unless you have them in line. I have shown all of this with methanol. It does not have to be methanol. It can be any alcohol. Right? You can make an ethyl acetal. You could make an ethyl and a methyl acetal. Right? This goes back to the stereochemistry question, right? If I have methanol and ethanol in there, I could have an OET and an OME hanging off that carbon. That would be weird. You wouldn't normally do that, but you could. You could also do a diol. This is pretty common. And you'll see this. Promise this is the last thing. You can take a diol, so a molecule that's got two OHs on it, and if those two OHs are in position that you're going to make a 5 or a 6-membered ring, you can make a cyclic acetal. Yeah. All right, that was a lot. There was a lot of stuff there. Once lab is over, I'm going to get this video up online. I'll suggest some problems. You guys have had a nice little break after the exam and not working problems. Next week, you can expect there might be some in-class quizzes. Hang on just a second. I'm going to talk about business for a minute. From this class, I want you to sort of, go back and think about the general nucleophilic attack on carbonyls under basic conditions, acidic conditions, be able to identify them. You should be able to do the mechanism. I say by Monday, you should go do the mechanism for hydration under either condition. And you need to start working on this mechanism. The mechanism to make an acetal is not that hard. Break it down into recognizable pieces, right? We protonated carbonyl. If I'll attack a protonated carbonyl, we pull a proton off. We put a proton on. We lose water. You guys have seen water lost to make carbocations a whole bunch of times. Nucleophiles attack carbocations. We lose a proton. Like, don't try to put the whole thing in your head all at once. Break it down into smaller pieces. If this panel bugged you today or didn't quite sink in because it was getting farther and farther away from your lunch, and I've been talking for a long time, we're going to come back and talk more about how we use this in chemistry. This was a bit of a muddle even for me today, so don't worry about it if this bit didn't get in there. Really focus as you're reviewing your notes and thinking about working problems. Think about it. All right. See you in lab in a minute, maybe.